Hello and welcome to DevOps Days Boston. This talk is titled Kubernetes Second Week. The goal for this talk is to cover things that I thought would be useful for people to know when they're just starting to learn Kubernetes, right after they have learned about what Kubernetes is about, things like pods, deployments, and some of the basic things. And this talk came about from the frustration I had when I was learning about Kubernetes, and I found a ton of resources for the basic intro level things, and also there's a lot of resources about very specific things you need to do, but there is not too many resources about things that you need to know from taking your knowledge from the basic intro level things and bridging the gap for learning the high level, really advanced topics. If you'd like to get access to the slides, this is the link to the slides. It's tiny.cc/k8s-second-week. If you'd want to look at the source code for the examples I'm going to be using, it would be at github.com/moficodes/k8s-second-week. Feel free to follow me on GitHub as well. My name is Mofi. I'm a senior developer advocate at Vonage. I work on their client SDKs, collect stickers, and write Go and JavaScript code. I can be found on any social media at Moficodes, so if you'd like to connect with me after, feel free to do so at Moficodes. So jumping right in, Kubernetes is something that manages your resources to run your container-based application. When you're running a bunch of this application in the same Kubernetes cluster, one of the things that immediately Kubernetes needs to solve is how do I make sure that my application is not affecting some other application by taking on too much resources. To control that kind of like starving neighbor problem, Kubernetes has this idea of resource quotas. Resource quotas, simply put, your application is asking this to the Kubernetes, give me X amount of RAM and CPU in Y increment. What it looks like in our favorite language YAML is you have a pod, you have some spec, your container. In this case, I'm deploying an Ubuntu image, and I have this resource that I'm asking for. I have a request of 2 gigs of RAM and 0.1 CPU, and my limit is set as 10 gigs of RAM and 0.5 CPU. What that means is when I'm starting my application, I would only be asking for about 2 gigs of RAM and 0.1 CPU. As time passes, if my application is requiring more and more resource, I will be requesting in this increment of 2 gigs of RAM and 0.1 CPU up to 10 gigs of RAM and 0.5 CPU. So how does Kubernetes then would incentivize us as an application developer to use these resource quotas and limits is by using something called a quality of service. So if you have no limit or request limit set in your application YAML, what would happen is you will get a quality of service class of best effort. Best effort basically means there was no limit mentioned, and this is the pod Kubernetes would be kicking first if it required more resources but it didn't have any left. Burstable is where you have a request set that is smaller than your total limit. So if you're asking for 2 gigs of RAM, but you're going to ask up to 10 gigs of RAM, you will be burstable. Guaranteed when they're both equal. The reason guaranteed is the highest level of quality of service you can get is because at deploy time, Kubernetes now knows exactly how much your resource you're going to ask for the lifetime of this application. And it lets Kubernetes also be able to pack things in different nodes much nicer because it knows from beforehand. Now it can reuse most of your node without having to guess whether or not this application is going to ask for more resource down the line. So let's take a look at an example of this. And it should be here. So we're going to look at resource quotas. So we have 3 examples. So this is the one that is best effort because it doesn't have any limit set. This one is burstable. It has just one limit set, and the request is a little smaller than that as well. And the final one has both the limit set, and they're both equal to the right thing. So K8s, resource quotas, K apply -f dot, and I deployed all 3 of them, and k get po-o YAML, and I'm gonna just grab the quality of service line from each of them. And if I do that, you will see that I get QF quality of service class of best effort from the first one, burstable from the second one, and guaranteed from the third one, as we expected, right? Like from the YAML that we had. So if this was a Kubernetes cluster with a lot of application, and I deployed some more important application with a higher priority class, this best effort pod might get kicked out because it is the least important in terms of all the other applications that I have. Next, we have the Kubernetes lifecycle methods. So Kubernetes, again, controls our containers, and Kubernetes have some lifecycle methods and lifecycle things it can do. So some of the ones we have is post start, pre-stop, sig term, and sig kill. Post start will be something right after your application is about to start. This method will get called, and you can do some action either directly via shell, or you could do something via HTTP. Same with pre-stop, right before your application is about to get killed, you could do some work via HTTP or some shell command. Sig term is the command Kubernetes sends when your application is about to get killed. Usually when Sig term command comes, most application will shut down immediately, but in your application, you can choose to catch the Sig term command and do something with it. Sig kill is your kill-9 in your Linux terminal. If you want some pod to die immediately, you can send a sig kill, and there is no way to stop sig kill from your application. So let's take a look at the example of using that in our applications. So we have lifecycle, and here we are deploying like a simple application. And what we are doing here, this is this particular application that I have written. I'm going to show you the source code just in a second. And in this application, what we do is post start, we run this shell command that sleeps for about 30 seconds and writes wake up to a file in a path. And pre-stop, right before the application is about to die, it sends a HTTP GET command to port 8080 in the path shutdown. These are the two hooks right now we're using. So before I deploy, let's look at the source code of what is supposed to happen, and we can have some ideas of what will happen. So in my life cycle, first thing we're doing is in my wait for post start function, I will use wait for post start if that flag is set to true. In our case, we do set it to true. Not this example, it will be, I'll save that here. Lifecycle, deploy lifecycle. So here I'm setting this particular variable to true. This is here just because I'm using the same code to do something else as well. But if that is true, we'll start run a for loop that is going to run forever until we exit. The first thing we do is check for the existence of a file in this path. And if it's not there, file doesn't exist, we just sleep for 5 seconds, log this out and sleep for 5 seconds. Also, if something else goes wrong, we also just log this out and sleep for 5 seconds. Once that is done, but the moment the file is created, we'll log out file is created, return from this function. Once we return from this function, now before our Go application starts, we call this. And once we are done doing all of that, we will print out whatever we need to print out. And that would be our application starting here. So before our application can start the HTTP server, we wait for the file to be created. This you can think of running some sort of like database migration. You can think of some files being available, like logs being available, whatever you need it to be available for the application to run properly. You can do something like that with your post start. And for your pre-stop, we're calling this function the shutdown. That's an HTTP handler on the path /shutdown. And what we do is we print out some things, and almost like we're printing some things in a for loop. You can think of this as like doing some cleanup if you want to send some last minute logs or clean up some database or clean up some log files, whatever you need to do. You could do that at the shutdown level. We're doing that with the HTTP method, but we could have also done that easily with another bash script. In our case, we're just showcasing two of the different ways you can do that. So let's just run it. Okay, apply -f deployment lifecycle and logs life cycle. I'm going to look at the logs from here. And because my pod is waiting on the post start, I wouldn't see any lifecycle method showing up. I wouldn't see any log showing up because I'm just waiting on that file being created for my application to start. So for Kubernetes point of view, that application hasn't started yet. So I'll look at the log one more time. I think 30 seconds almost have passed. So once 30 seconds has passed, we'll get that output. At this case, we do. We can see that the file creation has been completed. It prints about 6 to 7 times. Once that is done, we'll see eventually that file created. We're starting the application, and finally, we are starting the application in port 8080. So once the application is now running, let's okay, logs-f lifecycle. So what we'll do is just follow the log here, and we will delete -f deployment lifecycle. So we'll start sending the kill command, the Sig Term Command, to our pod, and that will initiate the pre-stop command, which we'll call the shutdown, get on the shutdown method. So you'll get to see the shutdown is initiated. So let me call that, and we'll immediately see that our logs showing that shutdown was initiated. We're doing some cleanup work. I'll go through this for loop, sleep for about 10 seconds. After that, we'll just print done, and we'll exit out of here. So our log fails because the log we're following just no longer exists. But the thing we're trying to showcase here was pre-stop got called, and we got to do the thing we wanted to do. The next thing we want to talk about is the Sig Term command. So Sig Term here is going to be the same application. It's the exact same application. But let's look at the source code and how we deal with Sig Term here. So the very first thing we want to look at, so the Sig Term, we have a separate application here, which is going to be source, OS signal, and main.go. So the application we have here, we are creating a channel for OS signal, and we're notifying we're catching the signal of OS interrupt or syscall.sigterm. So if we ever find a sig term, we'll be able to catch it here, and we'll be able to do something with it. So the first example we're going to showcase is the normal way it should be. If you want to use sig term, you can catch the sig term, do some sort of cleanup work, as we said before, like logs or database or what have you, and we'll sleep for 10 seconds, we'll call done, and our application was waiting on done on line 27. So when the moment we send something to done, we will be getting out of here and exiting the application. So okay, apply -f deployment. Oh, not this one. I actually should deploy here. Okay, apply -f deployment, and we're going to deploy Sig Term example. So our pod is running. I can do kget po. I'll see, and I have a bunch of other ones already running. I will actually get rid of them. Okay, source code. So I'll get rid of the other ones. Okay, get PO. I will see I have only one Sig Term here. And let's look at the log for the Sig Terms. Okay, logs-f Sig Term, and I'll be awaiting the signal here. So my code is stuck right now in this part, right? And this go routine is stuck on getting a Sig Term sent to it. Once it does, it will go through these 2 lines, send true to done, will be unblocked here, and we'll be exiting this function right here. So let's send a kill command there. So okay, delete -f Sig Term, and we'll immediately see that we are doing all sorts of cleanup work right here on this line. And once we do all of that, we exit after 10 seconds, and our application exits, and our delete command succeeds. Now, at this point, you might be wondering, if you can catch the Sig Term command, is it possible for us to then write an application that kind of ignores Sig Term? In the example would be just uncomment these 2 lines and comment out this 3, and can we do something or like basically do this? Nope, comment this and this. And what we're doing here instead is, instead of exiting the application by setting done equals to true, we're catching the Sig Term, going into this function, and just not doing what we're supposed to do, as in like exit the function. We're always keeping the function on. So okay, apply -f rogue. This is the version I'm calling rogue. So this is running, and I'm going to look at the log again. So we're looking at the log and awaiting signal. So what happens then if I try to delete this? So as you can expect, it was awaiting signal, but I'm going rogue, I'm invincible. This is the line that printed, but I'm not doing anything after that. So Kubernetes does have a backup to this system. It's called the Sig kill command. By default, the time is set as 30 seconds. So after about 30 seconds of an application ignoring the Sig Term Command, Kubernetes can send the Sig kill command to make it stop to force stop it if it needs to. So as you can see here, the Sig kill command got invoked after about 30 seconds, and my application is now killed. So this is one of the things you need to be careful of if you're catching the Sig Term command to do some work. If your work takes longer than 30 seconds, even though you caught the Sig Term command and you plan on releasing the application, Kubernetes might just send the Sig kill command and exit forcefully. So you can change the duration of Sig kill, but if you're needing more than 30 seconds to clean up and get out of the application, you might be looking at doing something different instead of using and catching the Sig Term command. So again, this exists, and I wanted to tell you this exists, but try not to use it as much, because the moment you start using things like Sig term, Sig kill, and like pre-stop and post-start methods, you kind of tie your application very closely to Kubernetes. And down the line, if you want to move to a more higher level platform than Kubernetes, or move to functions, or move to serverless, all of a sudden, a lot of these features might not be available. And if your application is depending too much on things like this being available, that might be long-term not a good idea. You are kind of tying yourself into Kubernetes. Kubernetes gave us the way to make our application more independent of platforms, and using those very specific features of Kubernetes, you are basically tying yourself back to Kubernetes in a very strong integration. So scheduling. So Kubernetes is a scheduler at heart that gives you APIs to access resources. So if you have a bunch of nodes on its own as separate VMs or separate computers or in a data center, that's not much different than what Kubernetes has access to either. But where Kubernetes really shines is the ability to use all of those resources intelligently to make sure that all your application gets the resource they get to run. So when you're using this kind of resource, sometimes your nodes might be mixed. What I mean by that some nodes might have GPU availability, some nodes might have SSD as storage, some nodes might have bigger bandwidth of network, and different things like that. And depending on what your application needs, you might want to deploy certain application on certain nodes, and also might want to keep certain applications out of certain nodes. For example, if you have a machine learning based application, you probably want to keep the GPU node available for that application for Kubernetes, versus if you have an application that doesn't really care where it gets deployed, it has very minimal requirements, you might not want to deploy that application onto the GPU node where it might not be able to use the GPU but using up that node space. So to control things like that, Kubernetes has a few different aces up its sleeve. These are called affinities, taints, and tolerations. So affinity, as the name suggests, is you can add certain affinity towards certain things. You can add an affinity towards a node. You can say that a node would be more likely or wanting to be deployed. An application might be wanting more to be deployed to a certain node, or you can also say application wants to be deployed closer to another pod. There's the opposite of affinity as well, which is called anti-affinity. You could say my application would be trying to not deploy it in a particular node, or not deployed in a node which has a certain pod. You can also have things like taints and toleration. So taints are a way to mark your node. You can say taints like no schedule and things like that. Once you taint a node, no other pod can be deployed to that node. But you can also have tolerations in your application and can still deploy certain pods in the node that also has a taint. So let's look at example of some of that here. So let's first look at the node selector. That's the most basic way of controlling where your application get deployed. So in this one, you're basically just saying, I want my application to get deployed in a node that has a label GPU and the value is available. So this would probably work in many cases, but it doesn't give you much of a fine-grained control. It's a yes or no question. Does the node has GPU? Does the node has available label GPU? Yes, deploy it there. If it doesn't, no, don't deploy it there. If you want a little bit more fuzzy control, what I mean by that is if you want a little bit more control where you would like to be in a certain situation, but you are okay not being there, or you would like to check for it at the beginning before you deploy, but once it's deployed, it doesn't really matter all that much. In that cases, you want to look at affinities. So in this case, you have this affinity here. That definition is quite long, but I will break it down for you. I'm going to also move this a little bit that side so they can read it in one go. So this is the whole affinity. So we have this node affinity defined, and under the node affinity, we have two different sets of things. So number one is the required during scheduling, ignored during execution. This is when if this particular affinity is not met, your pod will just stay on pending. It will never deploy. So it will just stay on pending until one of your node has this label. If it can't find it, it will just stay on pending forever. This one, on the other hand, is more of a soft condition. You are saying, I would prefer to have a node that has this particular label, but if it doesn't have it, I would still like to be scheduled. You can also set on weights on your preference. So the higher weight means the particular preference gets higher priority. So you are giving, let's say in this case, you want a location preference of US East or US South. That is a weight of 5. And number of course is a lower weight. And that's how it's going to get calculated. It's going to get totaled up, and you are going to see, so this one has a 5 times more priority than this particular one. It can just always keep adding more preferences with different weights, however it makes sense. This usually in practice, I don't see too much usage of, where you want to have a very, very like complex algorithm of weights and preferences. But it's still good to have knowledge of, because when you're trying to deploy your application and you kind of want to have an order of requirements met to be deployed, and there are certain deployments, certain conditions that are more important than others, you could do that via weights. You can also have pod affinity. So in this case, we're deploying Redis that we're going to use as a cache server, and we want to have a pod affinity. If you don't know what this, so we're doing something called the pod anti-affinity. So because we're deploying this Redis cache server, we want to make sure our Redis servers are kind of distributed. They are not next to each other. So in this example, let's say I have a 3-node Kubernetes cluster, and I deploy this Redis with this anti-affinity. What would happen is, because so the label itself is the same label that my Redis store has. So because they have anti-affinity against itself, they will be distributed in 3 different nodes, not the same node. We can also look at the pod affinity and how do you get a certain pod next to some other pod. So in the same example where I have a Redis store and they have pod anti-affinity, I now have another application, which is a web store, some web application that is using the Redis store. And what would happen is, I am first setting an pod anti-affinity onto itself. So the web store goes into 3 different nodes. And just to make sure each of my web store gets deployed next to a Redis store, we also add affinity to the affinity towards the Redis store. So what would happen is, if I, let's say, have 5 nodes now, and I have 3 of those nodes having 3 different Redis store, then I give my application at pod anti-affinity to itself. So they will be trying to go to 3 different nodes. Then I add affinity towards the Redis store. Now it should deploy my 3 pods into the same 3 nodes that has the Redis store. So what would end up happening is, out of the 5 node cluster, only 3 of the nodes will have both my Redis store and the web application. Thus, because the web application is using the Redis store, and if they're in the same node, the network connection is going to be faster. Taints and toleration. So if one of my node has a taint of no schedule, I can add a toleration to my application, and they will then be scheduled, even though there is a no schedule taint. We can just tolerate that particular taint. Okay, so descheduler. So Kubernetes also has a descheduler. Kubernetes can kick things if needed. If it is running out of resources, it can start kicking things. And the first things to go would be the best effort pods that we have no limit and no request. They will be very lower priority. They can get kicked first. So some of the things that Kubernetes doesn't kick are the critical pods. You can mark them with annotations. Orphan pods, you can if you just deploy a pod by itself that doesn't have any controller, Kubernetes doesn't really have any way to control the number of them, so that doesn't get kicked. Daemon sets. So daemon sets are a special type of collection of pods, a special type of controller that makes sure only one copy of that pod is running per node. And finally, pods with storage. If you have a pod that has attached storage, that pod wouldn't get kicked automatically because, again, if you have some storage data stored in it, if it gets kicked, it will be difficult to bring it back and sync it again. So Kubernetes decides not to kick them unless absolutely necessary. So usually Kubernetes won't kick anything if there's room for adding new things, but this will only happen when Kubernetes is running out of resource to deploy more higher priority things. So another type of things Kubernetes does have are jobs. So jobs are like you can think of jobs as doing a batched work together. One of the example of job could be, let's say you have bunch of images that you need to either label or create thumbnails for or do some sort of optimization on. Instead of every image being done real time, you could just after the end of the day, you can run a job that collects all the images throughout the day and run some optimization or some processing on. On the other side of jobs, you have cron jobs. So cron jobs are similar to jobs, but instead of doing it manually, starting it manually, you can just run it as timed every Thursday or every day at 12 o'clock at night. Just run this cron job. Cron jobs are super familiar to folks that are into the Linux administration. And the syntax for cron jobs in Kubernetes are actually very similar, are exactly the same as cron jobs you would know from Linux. So let's look at a couple of examples. So let's look at jobs first. So in this case, I have a job that is running a busy box and running the sleep command on it and sleeping for 3 seconds. And I want 10 completions of that job. So one of the things I can so this will spin up one after another 10 different busybox container and sleep for 3 seconds and finish the pod. I could also make it so that it runs multiple things at parallel. In this case, I'm setting parallelism 2, so at any given time, it will spin no more than 2 pods. I could also add some sort of deadline, in this case, 10 seconds. So if I sleep for like 15 seconds, after 10 seconds, the pod will actually get killed. So this will, setting a parallelism limit and setting a deadline will help us to not spin up too many pods that uses up too much resources. On the other hand, we have cron jobs. Cron jobs are exactly the same way, except it does have a schedule, and it runs on this particular schedule. I can't for the life of me remember what this cron schedule means, so I just use some online services to see what this is supposed to mean. But again, whatever interval you need to, you can just figure that out and put that here. And at that interval, Kubernetes will spin up a container, it will do the thing, and it will go away again. Okay, after cron jobs, we have daemon sets. Once again, daemon sets, as we said earlier, is just per node, you get one pod, and that pod will continue to run. If you add more nodes, you'll get more copies of the pod. If you delete nodes, you'll get, pods will go away. You could replicate what daemon sets does with deployment and adding anti-affinity to make sure your pods are spread out among all the different nodes that you have. But I think that is if your node number goes up or down, that is difficult thing to control. But versus daemon set, where the daemon set controls and makes sure there's only one pod per node. Before we talk about init containers, though, let's look at an example of daemon sets. So we do have an example of a daemon set, And a good example of Daemon Sets is where you are trying to deploy something that is supposed to be collecting metrics and logs for your Kubernetes cluster and the nodes. So having one FluentD service running per node is useful so that you can send the logs to FluentD from any application. Each of the application will have access to the FluentD running on the same node. So let's talk about Init Container. Earlier, we talked about how you shouldn't be using the post start method because that just creates a binding to Kubernetes that is not good for portability. For those kind of actions where you need to do something before your application gets started, Init Container is extremely useful. So what Init Container is, it's a container that will run before anything else in your container. So let's look at an example. I think that'll make it much clearer. So we have, so init container should be init containers right here. So we have a deployment, and what this deployment is doing is deploying our application, which our application in this sense is just a HTTP web server, which will be serving files on var www/html. But what we want to do before this does it is run an init container that downloads this code, which happens to be a very simple HTML page, and clones it and puts it in the path where HTTPD would be serving from. So before my application gets to start, this gets called and this git link gets cloned. So that is this thing right here. It's a very simple HTML page. Only thing it has is this few lines. So let's deploy that and see what that does for us. So I'll go back, init containers, okay, apply -f deployment. I'll just deploy both of them at the same time. So if I were to look at get PO, I will see that I have the init container running, and a couple of things are happening. I have 0 of 1 ready and init 0 of 1. So there's two different things. This 0 of 1 is our container that hasn't started yet. And this status init being 0 of 1, that means my init container is about to start. If I go back and run it, look at it again, by now my git clone is successful, my init container finished, then my container got to start and my application is ready. So if I look at get service, I will see my application has a node port of 31640. So I will go to my browser and go to localhost this, and I should be able to see my application. Again, this is a very simple application, and it's just Kubernetes second week, DevOpsDays Boston, which is great. And so this works fairly well, and you can see this. Again, this example was not probably the best use case of init containers, but you can see things like if you needed to run some workload to set up some databases, some file path, anything that you probably don't want to make your application know or application do, where it creates a dependency, you can kind of pull it out and make it an init container thing, so that now your application is kind of independent of the extra work you need to do, and you can get that work done by any other means if you down the line want to change that. So the other thing in Kubernetes, and it's a very useful and powerful feature, is the sidecar pattern. So sidecars are containers running inside the same pod as your container. So every time, if you learned about pods in Kubernetes, one of the things that might have been surprising to you is that pod is the smallest deployable thing in Kubernetes, not a container, and pod happens to be a collection of containers. And I think when you have, well, not I think, the moment you have more than one container in a pod, every container in that pod is a sidecar to the other containers in that pod. So let's look at an example of what a sidecar can do for us. For the same example we just saw, we'll see this example again. So what we have here instead is our application. In this case, we don't have an init container, but in our containers, we have two different ones. So the first one is this CentOS HTTPD. I'm just trying to serve this var www.html folder. And we have a second container, which is the same container as before, but this time it's a sidecar, and it is running a command of git clone every 15 seconds. So it is just on a loop. Every 15 seconds is just running a git clone command on the same repository. And what we can do with this is if we make any changes to this, after 50 seconds, we're going to see that change live updated into there. So it's almost like a very dumb version of a CD pipeline where we're running a CD pipeline. This is going to be sidecar. Okay, apply -f dot. And we will, our sidecar created, which is great. So I can get get service. I will see that my sidecar has 32654. And so if I were to go back to my browser, I can go to localhost 32654, and this is running here. Now, this is now different than what the init container was doing, but the cool thing we can do here, let's just say we want to update something on this page. So again, this is Boston, but it's also 2021 version of it. So I'll add that, I'll make that change. The moment I commit this change, I'll come back here. Again, every 15 seconds, the pull happens. So I don't know if it happened yet, but let's just wait about like 5 or 6 more seconds. And if I refresh, you could see that my updates are now live on the website. Again, this is not how you should do CD, but this is one way you can look at how sidecars are keep updating the data my application needs without me having to do some like hacky thing to update those things. Some of the other places sidecars are extremely useful are in the adapter pattern for Kubernetes, where let's say you have some sort of log collection that wants your logs to be in a certain format, but your application generates them in some other format. So you could have a sidecar that reads the logs from your application and converts it and pushes it off to some other place where your application doesn't have to be dependent on the specific log format. You can do that via the sidecar. Another place sidecars are extremely useful are in service meshes. So for service meshes, what we do is we have a sidecar that will catch incoming network traffic, gather metrics. You can apply policies. Both Istio and Linkerd, the two top service meshes out there, uses actually the sidecar mechanism. So sidecars are extremely valuable in that sense. Let's talk about some of the other things that we have access to. So secrets, again, Kubernetes does have a version of secret management. The issue with it, though, is that by default, secrets are stored as base 64 encoded strings. So you don't necessarily get much of security from the secrets. The word secret is a bit misleading. So you might think you can store like your passwords or access to your database, all that stuff in secrets. But if anyone in your Kubernetes cluster is not to be trusted or shouldn't have the permission to see those things, having those as secrets means they can just base 64 decode it and take a look at the secrets directly. The suggestion would be to use some service like Vault to generate secrets on the fly and pass it onto your application instead of using like a hard-coded and long-living secrets in Kubernetes. But if you have to use secrets, make sure you're encrypting your etcd database at rest so that no one can read the secrets as plain text. And lastly, the thing I think you should know if you're trying to get to the next level with Kubernetes is config maps. Although we can pass environment variables directly on our deployment YAML, if you have a bunch of different one of them and you want to keep them in an organized manner, config maps are a great way. Config maps are just key value pairs. It's an object understood by Kubernetes as well. So you can just create the same config map, different versions of the same config map, pass it onto your application and have different environments set up that way. That makes it very quick and easy to keep it in the same location to update and upgrade, as well as test out different configurations without having to like manually change things on the YAML every time. So with that, this is the end of the talk. This is, I think, all the things I wanted to talk about in terms of what I think you should know as the second week learning for Kubernetes. This was not meant to be all in, get everything learned about Kubernetes, but more of a, like, you should know this to be a better user for Kubernetes. And with that knowledge, I believe you can now go forward and learn more about Kubernetes and understand where Kubernetes can help you use this service better to make your application deploy faster, more secure, and utilize more of your resource that you have available. I have been Mofi, and you can find me on social media at MofiCodes. If you have any more questions after the fact, you can reach out to me on Twitter. And if you just want to connect or have any feedback on the talk, please feel free to reach out and drop me a message. Thank you so much to the organizers for letting me be a part of this conference, and thank you so much for listening so far. Have a wonderful day.
All right, thank you, Mofi. That was great. We got, I think, a lot of great material to chew on, figure out how we'll use in our organizations as we bring it back. I've got a question for you just around big nodes versus small nodes in your cluster, because this is eventually, I think, a growing point that everybody hits. Do you have an opinion on which is better when you would use few big nodes versus lots of small nodes?
I think, I mean, like, I'm going to give a terrible tech answer. It depends. But I think, for my opinion, I would probably start with few bigger nodes before smaller nodes, because once you're trying to move to Kubernetes, one of the problems everybody faces is that the existing application happens to be pretty big and you want to just move to Kubernetes. And if you are not understanding resource quota, which I talked about earlier in the talk, you might have to over provision at least to get the application running. So in that case, you might deploy on a small node and your application needs more resource. All of a sudden it gets out of memory and killed. You don't want that to happen. So bigger node is probably easier to transition over to, because we're coming from, if you're coming from a big VM kind of a world, it's going to be probably easier transition. But over time, once you understand your application better, that's when you start using affinities and kind of controlling where your application goes, all that fun stuff. That should come a little bit later when you have a better understanding of your scope of your application, what resources it needs, and how do you limit kind of this over node network chatter, right? If you have an application that needs to talk to another part of the application, another pod, putting them in the same node kind of helps you not going over the network to talk to another node in a different data center even. So yeah, so I think for number one thing is, does it work? So make it work. It's easier to make it work in a bigger node. Then how do you figure out how to improve the latency, improve deployment time, improved testing, and all that other fun stuff. So yeah, start with big node, but eventually right size it as you need to.
Yeah, that's a really good point about sort of growing in your cluster as you grow your organization's competency. I really like that. We've got an audience question from username, I don't know if I'm going to pronounce it right, but Adhengra. We've got, thanks, Mofi. Can you describe how to use readiness probes in conjunction with init containers?
So readiness probes checks if your application is ready for taking in traffic. So init container happens before that. So if you have a readiness probe, let's say you have a readiness probe that is checking that your application's /health is returning 200. So init container is doing something before. And the example I was talking about, let's say you have a database that needs some seed data to be populated. That happens in init container. Readiness probe doesn't necessarily interfere with that particular side, because init container will run, do whatever it needs to. Then your application is ready to start. Then the readiness probe checks, does your application certain path returns 200, or you can also do the bash command to check a file is available or anything you have. So in that sense, init container you can think of as the same thing you'd have done in your application hard coded to do something, versus in a container now you can swap it out anytime you want. So in that, because it's just happening outside the scope of your application, you have a lot more flexibility. So I don't think they're interfering or fighting for the same space in any way.
Got it. We have another audience question from Brian the Lion. And Brian says, really interested in CRDs. Actually, my director is just whispering in my ear that we should wrap up Q&A. So Brian and anyone else who is interested, we are going to start a breakout with Mofi in the talk breakout section in Discord. So feel free to come over and we'll handle that one first. And again, thank you, Mofi. We hope you're enjoying the conference today, and I'm going to kick over to Emily for our last talk.